This meeting is being recorded.
Again, Andrew, we have to find a way to get your voice on there. So we want to make sure that this really is a cornerstone stoichiometry problem, that we understand how to tackle limiting reactant when we're asked for excess reactant as well. And I know I just had asked us to really try that homework problem. We're going to open the floor to any questions or concerns. And then we'll demonstrate that, okay, we're feeling better about this by answering the same kind of a problem where you're looking for the mass of one of your products and then also ask for the mass of the excess reactant. All right. Then the next type of Stoich problem is where you're asked for or given percent yield. So what is that? And then we'll practice. That probably will be our first period together. Then the next and last layer of stoichiometry, I've come up with that name. I think that is the best name for this type of problem. It's not the hardest stoichiometry. It's not ton of work stoichiometry. It's just we're given more than just a simple mass of a reactant or mass of product. And we just have to make sure that we can find the relationships from the given to then tackle the stoichiometry. And as long as you are engaged and paying attention and asking any questions that you need, you'll be fully equipped to kill these kinds of problems. Keeping in mind, this is like the last layer of learning. We will practice tomorrow and keep practicing and doing some lab work next week. And then you'll show me your problem solving next Friday. All right. So we'll get really, really good at these problems. We'll learn and get some practice with these kind and really focus on these into tomorrow. Okay. Question on agenda. So first, your chapter 8 assessments. I want to give those back and then we'll start into the agenda. So I'm going to pause this for a second. Okay, let me just find our page. Okay. Did anyone have trouble getting the reaction? So we are, of course, okay, just to quickly go through it. So acetic acid we know begins with hydrogen. Acetic was acetate. +1 -1 is reacted with aluminum hydroxide. +3 -1. We know it's going to be double replacement. I think it's easier here, but you have the choice to write water as HOH. You can also write as H2O. I don't think we got this, or did we? I can't remember. And then because there's hydroxide and hydrogen, we can look at those as clusters when you're balancing. So we'll need a 3 here and then AlC2H3O2 3. All right. Now, Luke, how do you know this is a limiting reactant problem? How does it identify itself? Do you want to phone a friend? Masses of what? Because they could be the same mass. It could be 100 grams, 100 grams, 20 grams. So it could be the same. Yes.
Because you're given 125 grams of acetic acid and 275.
So, because we're going to have other problems where you have 2 givens. So can you just be a little more specific? We have 2 givens. How do we know it's a limiting reactant problem? Grace? We have 2 givens and they are both reactant amounts. Yes, Luke? All right. So we need to put in the work. There's no way around it. We need to figure out, you know, what the limiting reactant is. And there's at least two different approaches, and they all involve the same amount of stoichiometry. So we just can't get around it. So we just got to dig in and do the problem solving. All right. So what I did, and I'll go over the numbers, write it on the board if we need. Okay, why can I tell, if I can tell with your mask on even, that you're turned off? Turn yourself on, turn it back on. Okay, you're here in body, but not in mind. I can see it on your faces. So we're gonna go from one mass, and I just chose to do the first reactant, and that gives us 141.6 grams of aluminum acetate. Mary, should I do this on the board? Can you see it big enough on this? If anyone wants me to do it, just let me know on the board. Because definitely with my earlier class, they were making errors in their formula masses. So that mass of acetic acid gives us 141.6 grams of product. And then we do for the other reactant, and that will give us 719.6 grams of aluminum acetate. We, of course, will only get the smaller yield. So the answer to the first problem is 141.6 grams. Anyone want to see more work than I'm just showing on the board? Okay, then the next layer, finding excess reactant, and you could go one of three ways. We should have gotten that 220.9 grams of aluminum hydroxide remains, is left over. 220.9 grams of aluminum hydroxide. I chose the third way that we talked about. Whenever the limiting reactant is identified, which remember, the limiting reactant limits the product. Whatever gives you the smaller mass, that is the limiting. So I know my acetic acid is my limiting. It's in control of everything. So I calculated from the limiting reactant to the excess reactant, and that's how much reacts, and then subtracting. Could have also calculated saying, I know I'm going to get this much product, but then back calculate to the excess reactant, find out how much is needed to make that, and then subtract. Yes, sir.
You should have worked for like the how to get 54 bucks.
Definitely. Starting with what? So what makes sense to you? What makes sense to you? So just going to go ahead and pick this. All right. Now, how do we know if the problem is a percent yield problem? Well, a couple things. One, the wording will be there. It will say percent yield somewhere. Either we are asked, what is the percent yield? Or you're given a percent yield, has an 85% yield. So the terminology will be in there where limiting reactant problems, right, Roman? It doesn't say like, be careful, limiting reactant problem. All right, percent yield. You know, you don't have to ever memorize equations. I will always give them. So percent yield. We find it by taking, and it's interesting that we call it actual, where previously we probably would have called it experimental. So your authors and most chemists, but we could call it experimental, but we choose actual instead, divided by theoretical times 100. So we are analyzing how good the production value was. Okay, Anthony, percent yield equation, yield, 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 yield 3 places. What is yielded in a chemical reaction? What do you mean? Can you just enrich that a little bit more? I totally agree. Okay. What you get from the reactants and the products? What things are yielded? Let's look at problem 1. Okay. So methanol can be produced. Anthony, would that be a reactant or a product? Yeah. From the reaction of carbon monoxide and hydrogen. Okay, methanol can be produced from the reaction of carbon monoxide and hydrogen. Okay, we need a 2 there to balance. Okay, Anthony, in that equation, what would we say is yielded? Yeah. Products are yielded. Remember we said that arrow could directly be interpreted to be yield. CO plus 2H2 yield. Products are yielded. So the percent yield is always talking about a product. Always. So to make cookies, you have your separate ingredients, the egg, the flour. When it says 3 dozen, it's talking about the cookie, chocolate chip cookie, not what I put together. Okay. So if we take a look, all right, if 75 grams of carbon monoxide, okay, reacts to produce 68.4 grams of methanol, what was the percent yield? All right, so I know I'm going to probably employ the equation actual yield over theoretical yield times 100. Okay, Andrew. We started out with stoichiometry where we were just given one given, and it was usually the mass of a reactant or a product. And then we would just do our unit conversion. We saw, let me reactant problems, 2 givens, and they're both reactant amounts. We know it's a percent yield because it says it for crying out loud. But what is different about the givens here? Unless you actually did the experiment. How on earth would you know what you actually got? Unless you performed it. How are you going to know how much product you're going to get in lab? So the amount of product, that's going to be your actual yield. Yield is always about a product. If you're told the amount of product you are getting, that's your actual yield. Luke, is that okay?
Yeah.
AJ, does that make sense? All right. Of the CH3OH. Okay, so we need to find theoretical. Remember, Tyler, theoretical, we look up in a book, maybe we pull numbers from the periodic table, or it's calculated. Okay, how do we find the theoretical yield for this problem?
You can start with a given, so 75 grams.
Okay. And then?
And then you find the molar mass.
And this will be 28.01 in every 1 mole.
And then you find the mole ratio.
Of what to what?
The It would be 1 to 1.
Of what to what?
Carbon monoxide methanol,
Why to methanol?
because that's the product that's being yielded.
And if we could have multiple products, but if we're given the actual yield of one of them, that's what we're looking for. All right, so then our last step, because our actual yield is in grams, then we'll need the theoretical yield to be in grams. And 1 mole of CH3OH is 32.05. And doing that math, we get 85.82. I'm running out of room here. So because I'm running out of room, I'm gonna do this then here. So my percent yield, I already have the equation, so I'm just gonna plug in my values, what I was told in the problem, divided by what I just calculated. Grams of CH3OH will cancel. Multiplying by 100 to make it a percent does not influence the sig figs for our answer. Could someone please share what they got? Oh, do you have it, Carter? Go ahead. Excellent. Excellent. And that would be enough. Again, I feel it's my job to show us best. And so officially, it would be 79.7% yield. Dean, when we are assessing percent error, what number are we shooting for? What would be ideal for our percent error value? As low as possible, as close to 0 as possible. Do we want that same? Do we want to be as close to 0 as possible? Why not, Roman? It is a ratio of what are we getting versus what we should be getting. Okay, if it says I'm going to get 3 dozen cookies, do I get 3 dozen cookies? It's not the difference divided by what we should be getting, which is percent error. All right, so we want this to be 100. And problems that I give you on paper, they're going to match reality that we usually are under 100%. Because how can we get more than we should in lab sometimes because we haven't fully completed a reaction? Lab-wise, we could be. So your answers, we can expect that they're going to be less than 100. Do we know on average, or can we guess? Madison, can you guess the percent yield of the combustion of gasoline in a car engine? Average. What would you predict? Knowing ideally 100.
85, probably lower, to be honest.
If you could find a way to make a combustion engine deliver an 85% yield, oh my gosh. Your family would be set, not that money is the answer, for generations and generations and generations. Average car engine, combustion at 3%. But I guess that's from point A to point B. Yeah, isn't that something? Isn't that something? Man, if you could pump that up to 5%, look out.
What would it do if it's a higher percent?
Then if it was you wouldn't consume as much gasoline. So your gas mileage would go up. You could travel many more miles per gallon. Yeah.
Travel forever. It's like
Well,
those
no,
things
but-
are expensive.
but just think, oh my gosh, you'd fill up your car. It depends on how much you drive and so on. But man, you'd fill up your car tank like every couple months instead of every week or something. That's something.
Right, and gas prices soar because they're not making so much.
Exactly. So it would be like $20 a gallon. Yeah, I know. Everything's in like ratio. I know. Yeah. So interesting. Interesting. All right. Now, I'd say 85% of the time, a percent yield problem, that's what we're after. Just like so many labs, we want to know what is our percent error. That's usually what we're after. The other type of percent error, we could be given that within the problem, but I'm going to save that for tomorrow. Okay? So I need 12 excellent, pump up your brain power engagement. So, you know, at the end of practice, when your coaches ask you to deliver, like you have to do a couple final laps or whatever, you dig in and you find it. So I know that you can do that. We need to have good thinking to do this one example problem. The complex given problems I'm doing in a certain order for a reason. If you in your packets, please, could turn to we're going to actually backtrack. Sorry. We are going to page 10. Page 10. And if you want, you can do problem solving below the problems, but I also want to bring your attention, page 11 is open. You can always help yourself to more. Okay. The last part of stoichiometry is what I categorize as these complex given problems. So 7, 8, and 9 will present that to us. Can we work our way through number 7 today? That would be my goal. Okay, so can you please read number 7 first on your own? All right. So that's kind of weird right off the bat. Grams of air? What? Oh, huh? I mean, grams of air. Is there a formula for air? So that's maybe where my brain's go like, what? Are required to complete the, okay, combustion. Now it seems like we're more back to chemistry of 93 grams of phosphorus. All right. You know, you never have to write down givens. That is the way that my brain helps to figure out how to attack the problem. So I'm just going to model for us what I write down, but you know, givens are never required. All right. How many grams of air? That helps me if I like know what I want to solve. So that obviously is like what I want my answer to be. Are required to complete the combustion of. So, okay, I'm reacting combustion, 93 grams of phosphorus. Now it's my habit, if I can write a formula, I'm gonna write a formula. Phosphorus, not diatomic, and I have 93 grams of it. You know, I like to write the amounts beneath the formula. Up to you, you don't have to do that. Oh, complete combustion of that too. Oh, so I must be making that? Diphosphorus, so now I have 2 phosphorus, penta, oh, that's 5, oxide. And then assuming air, okay, is 23% oxygen by mass. Okay, and oxygen, you know, I know it's going to exist as O2. All right, we're in stoichiometry, so we know there's going to be a stoic problem involved. So the first place my brain definitely wants to go is, okay, what is the chemical reaction? That's not a chemical reaction. Where's the oxygen? So Luke, what do you think, sir?
I'd say it would just be O2 plus P.
Yeah. So O2 plus P. Okay, keep going.
And then it would just yield P2O5. And then it would be 4B5O2 and then 2 P2O5.
Excellent. Excellent. Okay. So we have to be okay, because when I see combustion, I think hydrocarbon plus oxygen, we're getting carbon dioxide and water. We just have to realize where we need to go. I'm sure the author of the problem wouldn't mind being corrected. I would have just read required to complete the reaction instead of combustion. I think the author was trying to, get us to lean toward oxygen as our other reactant. Okay, so we know we're reacting 93 grams of phosphorus, but the answer wants air, but air isn't in the reaction. So what do we do? What do you think, Star?
Do the, wait, I was gonna say the percent yield backwards, but that doesn't make sense.
But you know what? The only thing to not do is nothing. So I'm so glad you gave an idea, because that's an idea. And if it's wrong, then we try something else. Great. So you're saying, okay, I know I'm reacting this. Can I calculate from this to find out how much of that I'll make, and then calculate how much of that? Would it be okay, Grace? Could we just calculate from phosphorus right to oxygen? Yeah, I love your idea, but we can just go. You can calculate between anything in a reaction. I know we've been going to product over the last couple of days, but you can go right from phosphorus to oxygen.
Would you get an oxygen and then multiply by 0.23?
Well, can I show us something? We want to problem solve this all together. We don't want to get an answer and then do something else. We want to do all of our math at once. This is the expectation. If we can create a conversion factor out of any of our givens, we're going to do it. Okay? 23% oxygen by mass. Remember when we were doing percent of an element in a compound, like percent of hydrogen in water, and we would find the mass of 2 hydrogens and then divide that by the mass of the 2 hydrogens with the oxygen and then multiply by 100. It was the mass ratio of element to compound. So when that says air is 23% oxygen by mass, can I express this as a ratio? I would favor the most cooperative numbers. If we are saying air is 23% oxygen by mass, isn't it for every 100 grams of air, it'll be 23 grams of O2? Is that okay? But could we also say, oh, well, there's 23 grams of O2 and 100 grams of air. Maybe that's, a more direct, that seems a little more clear. Yeah, if it's a mass ratio, why don't we just express it out of 100 because it's a percent? Now, maybe you're like, Ms. Garrett, that's just way too elementary. Then you want to do 2.3 grams of O2 in every 10 grams of air, or 0.23 in every one, whatever, like makes you the comfortable, but is correct. So what we really have, oh, you couldn't see that. I'm sorry. The other versions that I gave. So what we really have for this problem are 2 givens, the mass of phosphorus and then this conversion factor. All right, so let's dig in. And the way that you guys were saying is exactly the way we're going to do this, but we're going to solve it all as one problem. I would encourage us, you don't have to, but I would encourage us to always start with the non-conversion factor. Start with the non-conversion factor. So that's the 93 grams of phosphorus. And I surely hope our gut just is telling us, oh, just go right to moles. So phosphorus 30.97 in every 1 mole. Okay, where are we going now? Mole ratio. Okay, well, look. Now we're in terms of oxygen, but look what has air. It needs grams of oxygen. Okay, so every 1 mole of O2 is 32 grams. So I think someone said multiply by 0.23. Okay, that cancels, cancels, cancels. Okay, let the problem guide you. We don't want grams of oxygen, we want grams of air. So the 100 goes on the top. Yeah, and look at that. We get our answer. Because of the 93 and the 28, we're limited to 2 sig figs. And our answer is 520. 520. All right, ladies and gentlemen, on that same page, can I ask us to please answer number 1? Number 2, you don't have to do stoichiometry for. So number 1, we'll have to do Stoich, but number 2 is just starting to get us thinking about the other kind of percent yield problem. All right, look forward to seeing you tomorrow. You don't have to do anything but bring your amazing selves and homework tomorrow. But tomorrow we'll have a little celebration for periodic table day. You're welcome. Have a really good day. Here you go, sir. You're welcome. You're welcome. Eric, is that your idea?
No, it's hard.
Website.
There was like nitrogen in the product. Nitrogen in air. So we have to do more than enough. Like let's say nitrogen and oxygen.
Yeah, we want.
The problem's like
Okay, you know what? I have 20 more.
We'll see. Probably, we'll see. Have a really good day. Have a good day. Sophia, thank you for showing me your work. I appreciate it.